My name is Long Pan. I'm currently a third-year master student at Tsinghua University. And today, I'm going to present our paper, Your Router is My Probe, Measuring IPv6 Networks via ICMP rate limiting side channels. And let's begin with the background part. And actually, as we know, the IPv6 is becoming popular, but when it comes to the IPv6 measurement, there are some new challenges. For example, the lack of related resources like open data sets and the lack of vantage points. And IPv6 is also considered to be more secure in many aspects. For example, there's no IP ID in the fixed IPv6 header. And the huge address space of IPv6 also makes it very difficult to find some scanning targets. And our paper is focusing on one of the main challenges of active internet measurement is about the vantage point. Active internet measurement usually requires us to send and receive many packets on the VPs. And the fact that we cannot have VPs in all the networks, but many measurements cannot be done if we don't have good VPs. So our idea is how about we just using other devices as our vantage point? And let's talk about the ICMP rate limiting, which is the main topic of this paper. And ICMP, as we know, is one of the most common protocols on the internet. Some well-known tools like ping and traceroute are mainly based on ICMP. However, to prevent from possible waste of resources and ICMP flow attack, every IPv6 node are required by the IETF standard to limit the rate of sending ICMP messages. For example, you send 100 pings very rapidly, you may only get 30 or 20 replies. That is because the ICMP rate limiting. Usually, this is maybe a bad news for IPv6 measurement. But we found that the global ICMP rate limiting also opens up a new side channel. And this paper, we mainly propose a novel measurement technique based on ICMP rate limiting, and we call it iVantage. iVantage can, to some extent, use other devices as our vantage point, and then we can send and receive packets on those VPs. And I'm going to discuss about the iVantage. The first step of iVantage is we just need to find some vantage points, but they are not real vantage points because we have no control over them. We call them remote vantage points, RVPs. They are mostly Argus routers, and the process of discovering them is actually very simple. We just send probes to randomly generated targets. And because the targets are fabricated and most of them are unreachable, and then we can collect many ICMP error messages. And most of them are sent from the last hop router, and we call it periphery. And this is actually the RVP, the remote vantage point we will use in our subsequent measurement. And we are going to collect the data pairs, the target and the RVP. Just for example, for IPv6 prefix like this, and we send many probes and we receive many ICMP error messages. For example, if we send the probes to these IPv6 addresses, and we may receive ICMP destination unreachable because this IPv6 address is unreachable. We may receive ICMP destination unreachable from here. And we collect the two IP addresses, and this is our data pairs. And actually, we refer to some previous work on the IPv6 network preferred discovery. And our discovery, finally, we found about 1 million RVPs, and it covers about almost all the countries of the world. And the step 2 is we need to send packets on those vantage points, but we have no control over them. So how can we do that? A very simple and easy to implement way is we just send packets with spoofed source addresses to the RVPs. And then RVPs, after they receiving those packets and they are responding, they are sending their replies to the real targets. So actually, this target is our real target. We just use the RVP to probe them, just as if we had required RVPs to send packets to the targets. And step 3 is to receive packets on the RVPs, and it seems to be more difficult because we have no control over them. However, assume that the packets the RVPs receive will trigger ICMP rate limiting on them. Then we can know whether the packets are received by observing ICMP rate limiting on the RVPs. For example, the RVPs are receiving a series of packets, and for each packet, the RVP are required to respond with ICMP error messages. Then we can know whether the RVP had received those packets by checking the state of ICMP rate limiting on the RVPs. If it's triggered, and we can know from the local vantage point that the packets are received by the RVPs. And we apply this technique to several difficult and also very different measurement tasks. And all of them are very difficult if you have only one local vantage point. And today I'm going to introduce only the second one. It's about the IP reachability measurement. It is the most easy to understand one, and it is also the most difficult one because it relies us to both send and receive packets on our RVPs. And let's talk about the reachability measurement. Internet nodes always interconnected. In most cases, the answer is yes, but many causes like link failures and routing failures and internet censorship may lead to loss of reachability. However, measuring reachability between two nodes without controlling any of them can be really hard and even impossible. And there have been some related work, and most of them are focusing on the censorship, but our paper focuses on the network level reachability itself instead of internet censorship. And just suppose if we have control over either of the targets, this task is very easy. We just use one to ping another, and we can know if it's reachable. However, we have no control, but the process is similar. We need our RVP to send packets, and we need our RVP to receive packets, just in the way I have introduced before. And let's begin with a simple thing. It may help you to understand the basic idea of this method. For example, you are the black guy, and there's two guys. They are Alice and Bob. Let's suppose that Alice is in a very remote place. For example, she's going hiking and in a place that may not have good network coverage. And you may be wondering that, can Bob have a phone call with Alice? So actually, if you are Bob, you can have both phones. The task is very easy. You just call Alice and you will know the answer. But what if we have no control over Bob's phone? So we can use our technique. We first make a phone call to the Bob, just pretending I am Alice. And then the Bob will notice that he had some missed calls and he will make a phone call to Alice. And at the same time, we make a phone call to Alice or Bob because it's the same. If we found the line is busy, we will find that they are on conversation, and we will know that the connection between them is good. So this is the basic idea of this method. Let's come to the real thing in practice. For example, we have a local prober B, and this is the only real VP that we have. And we have two targets, target B and target A. And we want to know that whether target B can send packets to target A. And this figure, we can find that the target A is already an RVP, and this will make the process more easier. If neither of targets is an RVP, we should first find a proxy RVP as close as to either of them as possible. And the assumption here is that we found loss of reachability is unlikely to occur between two very close internet nodes. So we may find a proxy to represent those reachability. And then we may send probes to the unreachable IP address. This is just like the way we found RVPs, and we call such packets probe packets, because the packet A is an RVP. By sending those packets, and we can receive several error messages from packet A. And usually the RVCV1 is less than the number of probe packets because of ICMP rate limiting. And actually, this is the target RVP in the data pairs. And then we send packets to target B, pretending that we are the unreachable IP address X, and the target B will send the replies to the unreachable IP address X. And here comes two cases. If we call these packets noise packets. If this noise packet cannot reach target A, so the step 5 will not happen. If it can reach target A, it will, because the target, the X, is an unreachable address, and it will force the target A to respond with ICMP error messages. And we can know that whether the reachability between target B and A is good by observing the ICMP rate limiting states, because if the packets successfully arrive target A, and the ICMP rate limiting will be triggered or aggravated on the RVP, and we will find RVCV1 is greater than RVCV2. Otherwise, if we found RVCV1 is same as RVCV2, actually the noise packets in the step 4 doesn't happen. It's not delivered. So it doesn't make a difference. So we may find RVCV1 and RVCV2 actually the same. And our results also show that our expectation is correct, and this can have a relatively good precision and recall in multiple measurement. And here are another measurement application due to time limit, I cannot introduce them in detail. So these two tasks is also very difficult if you have only one local probe, but with the assistance of our RVP, we can achieve them to accomplish those tasks. And I will talk about measuring the rate limiting, because we may wonder how do IPv6 nodes implement ICMP rate limiting, and we may find there's global rate limiting, there's strict rate limiting, and there's loose rate limiting. And our conclusion here is that we found ICMP rate limiting is very prevalent. After all, it is required by the RVC standards. And we also found that the rate limiting of ICMP destination unreachable, this type of message is most strict and easy to observe. And from this, we can know that iVantage can make good use of ICMP destination unreachable without sending a large number of packets. And we also found that global ICMP rate limiting is very common, especially for the ICMP destination unreachable. And this means that iVantage can be widely used for different RVPs across the internet. And let's talk about the risk and the mitigations. The basic idea below this is that the global things seems to always be some kind of harmful, just like the well-known global IP ID counter set channels. It's a very classical set channels with long history. And global ICMP rate limiting is though less harmful, but also can be dangerous, and it will reveal some information that it shouldn't reveal. And also we found that sending ICMP error messages will expose itself. For example, at first, we don't have any IPv6 addresses, but we send packets to randomly generated targets, and we receive many ICMP error messages. And by this, we can find many active routers, and even they can be used as our RVPs. So this is very interesting. And the mitigation part is also maybe there's a non-global ICMP rate limiting, but is easy. It is an intuitive solution, but it may be difficult to implement and deploy. And the strict asymmetry limiting is more simple solution because it makes the difference before and after the rate limiting much less observable. And we also think that asymmetry error message should be strict because it exposes itself. It will lead to some privacy issues. And the limitations of our future work, and we are focusing on some more measurement application with this technique. Because in this paper, we just send the pins. Actually, we can see the other packets. And after that, we can infer the reachability of them by using the technique. And we also found that the behaviors of asymmetry limiting is also very interesting because different device may show different fingerprint of the rate limiting process. And the paper may include some more ethics, problems of ethics, and we talk about them in detail in our paper. And so this is my presentation, and thank you for your attention.
Just wondering if you looked at any block lists for IP addresses which have opted out of being basically part of large internet scanning. I know you talk in the ethics about that kind of stuff, but yeah, did you have a look at any of that?
You're talking about the block list of IP scanning or something like that. I didn't catch your point.
Yeah, so in previous research with large internet scanning, specific organizations will request that they don't be included in that. They might not want the traffic or for various reasons. And so some previous research have made lists available, so like ZMAP, I believe, has that kind of thing. Did you consider looking at any of that kind of thing to not include those as part of your scanning? Or did you get any requests from organizations requesting they don't be included?
Our measurement does not send such too many packets as far as I'm concerned. So unlike some ZMAP is because it focuses on the scanning, but our measurement may be something different than that. So.
Okay. Any other questions? If not, I have a question. So you present most of this work as a method for measuring internet traffic or internet things in the internet. And then at the very end, you've talked briefly about, well, maybe this also has security implications. So do you see this as a novel method for measuring things that have been previously very difficult to measure in the internet, or as a security hole that we should try to close as quickly as possible?
I think it includes both of them. I think first it is a quite novel measurement technique to accomplish some measurement tasks that cannot be done. And also there is also security and privacy issues, I think, because besides this paper, and there has been some papers on the same channels like that. And unlike our measurement may not seem so harmful, but I know that Chris worked on the CCS in the last year and another year that is more dangerous because it will reveal the open port and it can be used for DNS cloning, but that is more dangerous, I think.